Okay, good afternoon. Welcome to the afternoon session that is going to be on translating, using large language models to do proof translation. My name is Andy Gordon. I'm from Cogna and University of Edinburgh. It's my privilege to chair this session. We have two fantastic talks for you. The first one is on this title, Automatic Translation Between Proof Assistants, a case study by several authors, and Jules Viennot is going to be our speaker. Over to you, Jules.
Thank you. So hello, everybody. Today I talk to you about making Mini-F2F available in Rocq using an automatic translation process between proof assistants. So as you surely know, using large language models to generate some reasoning has gained momentum lately. So either in using natural language, so here you have an example of DeepSeek R10 reasoning, or using proof assistants. So here another example with NLIR Rocq proof generation. And because you want to be able to test the performances of your code generation methods, you need to have benchmark datasets. And that's exactly what Mini-F2F is. It's a popular benchmark dataset for ML-based code generation in proof assistants. It's made of 488 exercises from Olympiad and math classes. Here you have one such example about Angela's family drinking milk and coffee, and you have to show that there is 5 members in the family. And for the moment, Mini-F2F is available in Lin, Isabelle, and MetaMath. So here you have 2 examples of Angela's problem in Isabelle and Lin. But unfortunately, the dataset is not yet available in Rocq. So in this work, our goal is to use the informal description, the Isabelle version, and the Lin version of theorems, give them to LLMs in hopes that they will output a correct Rocq translation of the theorem. And so it's important to note that we don't care about proofs in this work. We just want to translate theorem statements. So first, let's talk about which models we use. We use 3 models from OpenAI and 1 model from Anthropic. And based on their number of parameters and if they display chain of thought or not, we rank them from worst to best. And as you may notice, there is no open weight model. So we have to use them as black boxes. This means that the prompt is our only lever for translation. So let's see what the prompt looks like. We have first a system prompt, which is the same for every calls to model. So each time we call a model, there is this system prompt, and it's the same. We start by giving some context to the model, telling he's specialized in proof assistance. Next, we tell him what his inputs will look like. And finally, we give him some instructions to start with. And next, we have a user prompt, which changes at each call. And this user prompt starts with the theorem information. So you have an informal description and the 2 other proof assistant versions. And you have some final instruction to be able to read the answer of the model. So in this work, we perform the translation of the dataset in 3 stages, each stage being comprised of several steps. One step being an attempt to translate all theorems that have not yet been translated. At the end of each step, a human must ensure all theorems are correctly translated. By that, we mean that we want to avoid some errors. For example, here, a model introduces a flowing function and a sum function as parameters, but we don't want that because we wouldn't be able to prove the theorem. So this translation is discarded, and if a translation is discarded by a human, it is put back with the untranslated theorems. And so conversely, this means that if a theorem is translated and validated by a human at the end of the step, we don't try to translate it anymore, and it doesn't appear on the next steps. So let's see what the first stage is about. It's called one-shot prompting. So let's look at the pipeline we used. We give LLMs some information about the theorem we want to translate through a prompt. LLMs output a Rocq version, and we send this Rocq version to Rocq to see if it type checks. If it type checks, the theorem goes to the human checking phase. If it does not, it remains untranslated. Looking back at the example from with Angela's family, here let's recall the description and other version, and a model successfully outputted a valid translation at stage 1. And here are the complete results. You see that there is 4 steps in this stage. With each step, we take a model of increasing efficiency. And as you can see, at the end of stage 1, we are already able to translate more than 60% of the dataset. Next, we move to stage 2, called multi-turn with errors. Let's look at the pipeline again. It starts as the one of stage 1, but this time, when a Rocq version does not type check, we give the error outputted by Rocq as a feedback into the prompt, and we ask the LLMs to output a new version, taking into account the previous attempt. And we allow a maximum of 3 attempts per theorem. For example, here is the paragraph we had to add to the user prompt to handle a previous attempt. So here you have an example where the first attempt was unsuccessful because it contained a syntax error, and hopefully the model was able to correct himself by the second attempt and give a valid translation. Let's look at the results. We see that there is 2 steps in this stage. Again, with model of increasing efficiency. And at the end of stage 2, we already have proven about 80% of the dataset. Let's go to the final stage called refine prompt. So at this point, we noticed that there were some pretty recurrent errors. For example, models had a hard time using complex numbers in Rocq. Here you can see a model hallucinating some libraries that doesn't exist in Rocq. Another common error for models was that it was difficult for them to really have a good typing when the theorem statement contain a lot of different types. So here you can see that the variable x doesn't have the right type for the floor function. And so what we did is that we added some Rocq tutorial and advices into the prompt. And we gave the LLMs more attempts to complete the translation. For example, in here you have a paragraph which is a mini tutorial on using complex in Rocq. Or here you have the paragraph telling LLMs to be really careful when using several types. Looking back at the previous examples, we see that the model was successfully able to correct himself and use the right library for complex numbers. Here we see that the LLM was also able to correct himself by changing the flowing function and adding some Z arithmetic to type check. And so looking at the result, we have two steps. In this stage, we focused on the Claude 3.5 Sonnet model, which was quite good. And we just increased the number of attempts. Here you can see 6 and 24 at each step. And at this point, we have successfully translated all the theorem but 10, which is quite satisfying, and the remaining 10 theorems were translated by hand. And so after that work, we asked ourselves some questions about model performances, about model inputs and model outputs. First, we wanted to see if a model that we consider better really performed better. So we did a study on comparing GPT-4 mini and O1 mini by selecting 100 theorem, 50 of which GPT-4 mini had translated at stage 1. And by running the comparison on one-shot prompting, which is the method of stage 1, it appears that GPT-4 mini is better than O1 mini. So is it really the case? We wanted to be sure, so we increased the number of time we did the one-shot prompting. And so collecting all the success of 3 one-shot prompting. From that, it appears that GPT-4 mini and O1 mini are equivalent, although O1 mini is supposed to be better because using a chain of thought reasoning. An interesting fact is that the vast majority of theorem were either both translated by models or both untranslated, meaning there is really a common notion of easy and hard translation for those two models. Next, we wanted to see if the result will change when we change the amount of information about the theorem the model had access to. So again, we did 1 and 3 one-shot prompting on the 100 theorem with different information in the prompt. What this ablation study shows is that, in fact, it seems quite better to just give the informal description of the theorem into the prompt rather than giving him some code. Once we give some code or only the lean version, it seems pretty equivalent in results. Finally, we were asking ourselves if the way the models translated theorem and wrote them into Rocq would make the proof harder to write. To answer this question, we asked Rocq users to review a batch of 25 theorems and ask them to answer this question. And what they told us pretty quickly is that it was a really hard question because, in fact, it's quite hard to know if a statement will make the proof harder or things like that. So we say that we relied completely on their judgment. For example, for some considered that there were no badly written theorems, and others consider half of the theorems we gave them to be badly written. The audit had also other benefits. For example, by helping us finding unnoticed errors. For example, here we have the Rocq example 4 that we already saw. In this example, we use there is a rational number A that is introduced, and we want to know what the sum of its denominator and numerator are. However, in Rocq, rational numbers are not, like the numerator and the denominator of rational numbers are not ensured to be relatively prime. So there was an error in the statement, and we had to manually add the numerator and the denominator into the statement for it to be correct. The audit also helped us to better align with informal statements. For example, if you have a problem where we want to show that maximum value for a quantity over T is 1/12, and in the translated version, you see that we only want to prove that this quantity is below 1/12. And after the audit, we choose to add some statement to the goal, stating that there must also exist a value where this quantity is exactly 1/12. And next, the audit is also useful to make the proof more uniform or appear simpler and prettier, for example, by currying. Here you can see that we have a useless import and useless hypothesis of strict positivity that we can remove. We also replace the squares by multiplication, which is more convenient in Rocq. And so far at the moment, about 25% of the dataset has been audited. And here's the answer we got. So we have only 1.6% of wrong statement, 6.4% that needed reformulation. So that is having a statement making the proof harder to write, or a statement that was not really matching the informal description. Next, we have 21% of minor changes, so essentially better syntax. And the rest needed no changes. And as you can see, reviewers proposed us proofs for about 17% of theorems. So that's nice. To conclude, we draw some main lessons from this work. First, the importance of feedbacks for LLMs. We saw a big improvement in performance by adding previous failed attempts. And we noticed that final errors are often due to the incapacity of a model to use the feedback. For example, here is a theorem part of the 10 theorems that were not proven. You can see that Rocq says there is an error with INR x plus y. And you cannot find this term inside your proof. In fact, it's INR nat.add xy. Rocq is simplifying it when printing it. And so things like that makes it harder for LLM to correct themselves. Moreover, we saw the importance of giving LLM indications. First, because when they had not much examples on internet, it was hard for them to write a good code. For example, when we scrapped on GitHub files containing natural numbers, real and complex numbers, there were only 500 files showcasing complex numbers against 8,000 or 80,000 for real and natural numbers. LLMs also struggle when there is several types or opening the good scopes, and telling them to be careful help them also. And so that's why we propose on our code also a supervision mechanism where you are able to tell the LLM manually what errors they have made. So finally, thank you for listening. We would greatly appreciate you helping us by participating to the Theorems audit. You can contact us at this address, and the data set is available at this URL and soon on Hugging Face.
Questions for the speaker? I have one to get us going.
Okay.
In your chart of, there were 10 theorems that you couldn't translate. Yeah. And our keynote speaker this morning was advising us to pay attention to the tricky problems.
Yeah.
So I wonder what you can say about it.
Well, it's, as I said, it's often when you look at the traces or the log of what the LLM proposed, you see that he often end up cycling and doing it again and again the same errors and being unable to correct himself, and just he doesn't correct himself when trying again and again. So there is not much. What was sometimes hard is that he was trying to propose some additional lemmas or definition, and so he proposed longer answer, and the longer the answers, the more chance he has to make mistakes. So I think that's the issue.
Okay.
Yeah, thanks. Yeah, I was also curious about those 10 that you did by hand. I was wondering whether or not you actually did this. Would you have found it useful to use that partial wrong proof? Like you were saying, the ways that it kept getting it wrong, but did it still give you useful information that would simplify the process of finishing it by hand, or was it just a mess?
Yeah, actually, yes. When starting to translate the final 10 theorems, I would look at the final attempt of the model to start from somewhere, because it's often typing issues or small keyword that it doesn't get right. So you have already most of the work already done. So.
And I guess similarly for the ones that took more effort, but that eventually got, was it, if you had been forced to use, say, the first attempt for some ones that eventually succeeded but failed at first, that would have also been fairly useful, probably?
Use the first attempt of the failed...
Yes, I'm saying other than the 10 that failed with everything you tried, the things that only made it at later stages of the process, if you had forced yourself to use the partial work that it got at first, that would have still been helpful, it sounds like?
Yeah. It's often quite right at the first attempt. And it's just doing some minor changes the more they attempt. So yes.
Thanks.
So there's a lot of work going on in translating, say, C to Rust with LLMs. So I wonder, in this work, is there anything that's unique to theorem provers? Because it seems you haven't translated any canonical solutions, so haven't touched the verifier.
So I think I don't really understand your question.
It seems that this is essentially a compilation problem here, right?
Yeah.
So you haven't really used the verifier, did you?
Well, no, not. Yeah, it's a good point. And actually, it's more to know what's a bit the state of the art of LLMs and writing in proof assistant. Well, in Rocq in this case, and doing that in proof assistant is quite easy because they have a really strong typing. They have very strong typing rules. So you also test the limit of theorems when they have few examples and a lot of restrictions to see if how do they perform.
Okay. Oh, one final question. Gentleman there.
Thank you. In this pipeline that you did, after the Rocq verification, did you measure how many problems the human verified as incorrect, but Rocq verified that synthetically was they translated was correctly without any errors?
No, I didn't write it down. I have it into the logs, but I didn't write it down. I think it's about maybe 5 or 10%.
10%.
I would say.
Thank you.
Something like that.
Okay, let's thank Jules. All right, and our second talk in this session is going to be presented by Gilles Baudart, and it's on natural language intermediate representation for mechanized theorem proving. Take it away, Guillaume.
Thank you. So I'm going to talk about a joint work that we did with Emilio, Gallego, Arias, Marc Lelarge, who is also in the room, and Laetitia Teodorescu, so she was a postdoc at that time with us, and she is now working at AdaptiveML, and I will try to fill in for her. Okay, so this is the overview. So the idea of this work is to try to push as much as possible natural language reasoning for mechanized theorem proving. And the key idea is that, as in the previous talk, we will rely on state-of-the-art LLMs, and mostly black box LLM like GPT-4o, DeepSeek, and Sonnet. And we want the LLM to try to explain and reason in natural language as much as possible, such that they can leverage external knowledge, hopefully a lot of different stuff about informal math, and then generate explainable proof. So at that point, I can explain the title. So it's called a natural language intermediate representation because the input will be Rocq statements like theorems or intermediate goals, and the output is also Rocq code in the form of tactics. But in the middle, we have natural language reasoning. And the hope is that it would yield more explainable proof, and proof where, as a user, you can intervene in the middle to fix some trajectories and do stuff like that. I will present 3 contributions in this talk. So the first one is Pétanque, which is a new lightweight environment to interact with the Rocq proof engine. So Rocq is a new name of the Coq theorem prover, and I will try to make an effort to say the new name. I will also present an interactive proof protocol that we call hierarchical proof templating that is reminiscent of some stuff that we saw this morning. And finally, we can couple our proof protocol with classic search algorithms such as beam search with a tweak. At this point, I want to make 2 disclaimers here. So the first one is that we did this work, this idea, and build the first prototype last year. So before O1 came out, so before all this craze about chain of thoughts. So that's one thing. And the other thing is that really, this is the motivation, but really what we wanted to see is how far we can go if we have no compute budgets and with very little money. So what can you do for automatic theorem proving in that setting? So, okay. So the first contribution is Pétanque. So Pétanque is based on Flesh. Flesh is a project that Emilio has been working on since 2019, and it's a new document manager for Rocq. And the idea of Flesh is that, can I use this? Yeah. So you have, Flesh is actually maintaining a decorated document, which is basically your Rocq proof document decorated with the state of the prover. So that I represent here using these green marks, okay? And whenever you do an edit to your document, say you want to type tactic, like apply LEN here, you retrieve the current state of the document, you send this state and the code to the Rocq interpreter, and you get back the next state, because the Rocq interpreter is purely functional. And then you can also use this next state to compute the next goal that is sent back to the user. Okay, and so Flesh implements a lot of very nice things like automatic memorization and serialization and deserialization tools, so you can use that to build your own prototypes. On top of that, Emilio built Coq LSP, which is a language server protocol for Rocq. And this can be used to add PL support for Rocq to modern IDEs such as VS Code or Emacs. And you get for free continuous real-time checking for your document. It's really fast. It's really nice. However, the LSP protocol is not very well suited for the tasks that we had in mind, namely building agents that can call the Rocq interpreter from Python. Document edits may be too expensive, so manipulated files explicitly can be relatively slow. And the LSP protocol requires a lot of communication for relatively simple steps because you want to be able to handle multiple panels in your IDEs, and we do not really care about that. So what Pétanque is really is just giving a direct access to the proof set and the tactic engine of Flesh. And here is, so we on top of Pétanque, we build a Python API that you can use for your own project. So here is a snippet of the API. Importantly, it's a functional API, so the Rocq state can be managed by the client application, but the client only manipulates IDs, so integers, basically, and the Rocq state is memoized on the server side, which means that you can very efficiently implement arbitrary search heuristic, especially those that can leverage the memorization mechanism. Okay, so to give you just a quick demo, but I don't have my computer, so it's not a demo, it's a screenshot. Here I can just write a simple file with a very complex theorem, and I can start a server and connect to this server and start a session with just a pet.start. Okay, and so when you do a pet.start, you get the state, which is an integer. And here you can see that if I print the state, I see it's just an ID and potentially a hash and a flag that says that the proof is finished or not. I can also retrieve the actual goals if I want to print them, but it's another API, it's a separate API call, so it costs something. And sometimes you don't want to actually check that. And I can print them with just a g.pp. And so I get this classic representation of the goal, okay? And then maybe the most important thing, the most important function for us in this talk is the run tag function, where we say, okay, given this state, can you apply this tactic, say induction here, and then I can retrieve the goals and print them again, and I end up with two goals as expected. And then what I said is that I can just run some tactics, and I don't care about actually what the goal is. I don't need to print it. I just want to check that I finished the proof. And at the end, I got something which is a current state and the flag proof finished equal true. Okay. And so I can leave everything like the entire Rocq state inside the server. Everything is memorized, and I can be relatively efficient. Okay. So with that, we have everything to build a first agent. And the first idea that a lot of people had to do that is to try to mimic the human behavior when confronting to a proof assistant. So you start with a current goal, and it's actually not so trivial example because we already see this theorem this morning. And you want to prove something like that. And what you do as a human is you start reasoning. And you say, okay, I know a lot of stuff about integers. I know how they are built. So I think I should try to start with an induction. And maybe before that, trying to introduce the variables. And this is exactly what an LLM would say. Then when you have that, you can send that to the Rocq interpreter and you end up with a set of next goals and so on and so forth. And the first agent that you can build is actually mimicking this behavior. So given a theorem or an intermediate goal, you ask him to explain, but in natural language, so you ask him to explain what is this goal. Then reason, so came up with a proof sketch saying what do you want to do at this point. And finally, and only finally, try to formalize it in the form of a set of tactics. Then you can take these tactics, try to parse them, execute them, and if everything goes well, you can serialize the results and send it back to the agent for the next step. Okay. And with that, what you can implement with whatever model that you want is some kind of Rocq-powered chain of thought where you can check every reasoning step with a proof assistant. So nothing really revolutionary here. However, if you think about it, we want to use black box LLMs that are typically only accessed through private API, so you need to pay for each call. And here, to generate a proof, I will need to pay a lot because I will need to pay at each step, at each tactics. I can see my I can see my tokens decreasing. Another thing is that these LLMs were not trained on this interaction mode, so there is very little chance that they saw the interaction tactics, current goal, tactics, current goals. What they saw at best are full proofs, so the theorem statements and the corresponding proofs. So the other agent that we designed is called hierarchical proof templating. You start with a theorem and you do the same thing that is reasoning in natural language. Here it says you should introduce thing and then conclude the proof and so on. And then you try to formalize a full proof at once. And so many of you, I guess if we are here, many of you already tried that with ChatGPT or Mistral or DeepSeek and so on, and it basically never works. So you end up with something that fails and you have different errors. But what you can do is try to templatize it. That is, you will replace all the errors by admits. So you are closing the current sub-goals. And then you reapply the exact same techniques, but on the sub-goals. And so this allows the LLM to do some kind of fine-grained reasoning on goals that are hopefully simpler. And the idea here is that maybe the first proof was completely wrong, but maybe the schema of the proof is correct and can be leveraged for the next steps. Okay, so here I can do this for the two holes, and I get the answer, and I can accumulate everything to have my final proof. Okay. So a little bit more on how the proof templating works. So it can be formalized as a simple state machine. So when you are reading a proof, you start in the OK state. And whenever everything is OK, you keep the tactic. And the bullet here, which is focusing on the first sub-goal, is also the tactic in this context. And then you end up with an error. And when you see an error, you replace the error by an admit, which will close the current sub-goal. And at that point, you need to drop all the subsequent tactics. Otherwise, you end up with something that is a mistake. And at some point, you can refocus the proof. So one way to refocus is just that the user is using the next bullet here to refocus the proof. But you have other way to refocus, like error messages that says wrong bullet is focused or focus next goal or something like that. So really what we are doing here is that we are piggybacking the error reporting mechanism of Pétanque. Okay. And so here is how it works on a complete example that I took from the evaluation set that we'll talk about in a few moments. So I'm trying to prove these random lemmas about some things that are regarding Turing machines. I will go back to that. So it generates this, and I have two errors. So the first error is the QED is failing, and the QED is failing because the proof is incomplete. And the second error, it might be not too readable here, but this is this bullet here. And the error says the current goal is not finished. So I can insert a hole in my proof to close the sub-goal, and then ask the LLM to generate the proof for this hole. And here I have almost a proof, but not yet. I have another error that says this proof is focused, but cannot be unfocused this way. So I insert another hole, and at this point, after 3 steps, the LLM is able to finish the proof. Okay. And actually, we are not that bad. So this is the original proof for this theorem. And you can see that the original proof was 16 tactics long, and the generated proof is 27 tactics long. Okay, so it's not too bad. There is a little bit of useless tactics in the middle. So these two autos are not changing the current goal. And we could also probably remove the brackets to decrease the number of tactics, but it's relatively okay. So rule of thumb is that we generate proofs that are twice the size of the original. Okay, so now we have our agents. And what we did on this example is basically a pass at one, meaning that we start with a problem, we do a succession of steps, and we end up with an answer. Might be good, might be bad. Maybe you want to bound the number of reasoning steps to 10 to not pay too much. So that gives you some answer. But we know now that there are more clever ways to do that. So one obvious idea is to try to solve the problem in parallel multiple times and accumulate the results. So this is the best of n of similar to a pass at k here. But we can do more than that because we are verifying at each step of the proof. We can verify our sub results, and so we can order all the candidates and favorize the most promising ones. So here, for example, this is how you would implement beam search with this kind of agents. At each time step, I have failing tactics, and so I can just restart from the most promising candidates and hopefully reach a solution faster than with just a pass at k. Okay, but at that point, there is an issue, which is how would you rank the possible candidates? So there is an easy problem. If you have templates that are failing, you can just discard them. But most of the times, you have templates with holes. They are all relatively valid. So how do you rank these possible candidates? And instead of trying to come up with clever heuristic for that, we just asked the LLM to classify all the candidates and return an ordered list of possible candidates. So this is something that you can find in the literature as LLM as judge, and this is just applies to formal theorem proving. We have no guarantee whatsoever that it's doing something meaningful, and yet it kind of works. So. Okay, so to evaluate our approach, the main problem that we had was data contamination. That is on particularly on academic data set, we were worried that since we are using black box LLM, they already saw the benchmark during training. And so what we were measuring would only be how well the LLM is able to just return a proof that you already saw. Fortunately for us, when we did this project, there was this BB5 project. So maybe you heard about this project. So this project is focusing on the Busy Beaver problem, which is how many steps a Turing machine can do before halting. And for example, BB4, the BB4 theorem states that a Turing machine can do 107 steps max before halting. And this is the main theorem for this BB4 project. So this is that for all Turing machines that stops, they stops after a number of steps that is below 106, because we start at 0, so 107. And there actually exists a Turing machine that stops after 106 steps. Okay, so this BB4 theorem is part of the more ambitious BB5 project, but this particular theorem was formalized in only one file that contains 260 lemmas and for about 8,000 lines of code. So it was perfect for us because it's a simple and grounded experiment. And for the proof search, so we give to the LLM everything except the proof up to the theorem statement. So in the context, you have all the definition and the previous lemmas. And we use our beam search with NLIR ranking with relatively small parameters. So the maximum number of steps is 10. So we can fill at most 10 holes at each attempt. The beam size is 3. And the number of responses that we generate at each time step is 4 for each of the 3 states that are in the beam. Okay. So here is a mandatory slide on the results. So we evaluated on the first 100 theorem because it's already cost a lot. And you can see here the models that are ranking according to their performances. And the thing that you immediately notice is that the bigger the model, the better the performances, which is kind of sad, but anyway. The other thing is that I put in gray the number of successes where the LLM was able to find the correct solution at the first step. So it corresponds to a pass at 4, basically, because we generate 4 possible solutions at each time step. Okay. And you see that with GPT-4o, we were able to reach 58% on this particular data set. I also report the price of these models, and you see that the best one here also is also the most expensive. So too bad for us. We also tried with Claude, Haiku, and Sonnet, but here we were rate limited by the API, so we were not able to complete the experiment, although Claude Sonnet seems to be the most promising one at this point, and it's even more expensive than GPT-4. Okay, and then I wanted to do a deep dive on the results with the best model that we had, which is GPT-4o. So for this, as I said, we proved 58 over 100 theorems. And as a measure of complexity, we count the number of tactics in the proof. And you see that as in the example that I showed at the beginning of the presentation, in average, we generate proofs that are twice the size of the original one. And we were able to generate non-trivial proofs, that is a proof that in the original file was 34 tactics long. So the main question is, what is difficult for the LLM? And at first we thought that as you go in the file, so the deeper you go in the file, the more difficult it will be for the LLM because it needs to leverage a lot of context, a lot of new definitions and lemmas. But actually, it's not the case. So here is a cumulative count of success. And here on X, you have the lemma IDs from 0 to 100. And you can see that there is no clear correlation. And in gray, you have the size of the original proof with random spikes everywhere, basically. So there is no real correlation between difficulty and where is the lemma in the file. Now, if you sort them by proof length, so we decided that the proof length was a good proxy for the difficulty of a lemma, you see that you have the shape that we expect, which is at the beginning, we were able to prove pretty much everything. And then for the most complex theorems, for this measure of complexity, we basically plateau, so we are not able to find them. And here are the generative proof lengths. And you can see here that it looks random. So it's not because the original proof was small, like 2 or 3 tactics, that we were able to generate small, small proofs. And you can also see here that we were able to generate some outliers, so we were really happy about that. Another view of the same results is here. So here I report the number of lemmas for each size of the proof. So we have like 9 lemmas where the proof is 3 tactics long. And in green, you have the percentage of generated proofs that are valid. So for example, we were able to generate 100% of the proof with 3 tactics originally, but only 50% of the proof with 5 tactics. And the interesting thing here is that we clearly have a cutoff at around 13, where we managed to do a relatively good job here for the tail of the distribution, and then basically it becomes quickly impossible for the off-the-shelf LLMs. Okay, and before concluding, I just wanted to show you some proofs that are generated. So this is sometimes you have good surprises. So this is a very simple theorem, and the proof that was generated was actually shorter than the original proof. Okay, so good surprise. However, if you look closely at this example, you might recognize something. So this is a really classic example. We are just proving that an involution is an injective function. This is an exercise that you can find in the Software Foundation book, for example. So it probably the LLM saw this theorem before. This is the best proof that we managed to generate. So we generated a proof with 43 tactics, and the original proof was 34 tactics long. So this is our main achievement on this project. And the amazing thing is that we were able to do that only after 2 steps. So so it generated basically 30 or so tactics, and then there was a simple mistakes at this point here. You see the hole at this point that it was able to fill at the second step. And again, if you look more closely at this example, you realize that it's just using stuff from the standard libraries. So, and this theorem is relatively obvious. So there is a good chance that this was also in the training set. And finally, there are some bad surprises. So this is a theorem where the generated proof is 59 tactics long, but the original proof was only 15 tactics long. And you see that we have a lot of useless thing in the middle. So this in yellow didn't change the proof state. And the interesting thing here is that if you look at the theorem, it uses the pop-back function that is defined in the file. And so this is an example where the LLM has to leverage the information that he has in the context. And here we can clearly see that it is struggling to find the proof. And we had a success, but only after 9 steps, which is really, really close to our 10 steps limit. Okay, so to conclude, some limitations. So first, B4 is only a very simple data set, so the style may not be representative of what we can do with theorem proving in Rocq. And as I showed you, some lemmas are, we are pretty sure that some lemmas are already in the training set. So you have to take these results with a grain of salt. Additionally, these experiments may not be reproducible. So some LLMs are only accessible through the private API, so we have no control on these beasts. The dataset is available on GitHub for more than a year now, so we are pretty sure that it was contained in the training set for the next generation, and there is a high risk of contamination. And finally, the cost of this experiment is not negligible. So this is why we limited the evaluation to the first 100 lemmas with a limited search, because it costs too much. Okay. And yeah, I will stop here.
Questions for the speaker?
Yeah, thank you. So in one of your first examples where you showed the two instances of auto that could be removed without changing the proof. So I can imagine even in situations where you can't remove it from that specific proof, you might still want a proof that doesn't have auto for various reasons. But then, so you can see everything that's going on in more detail. But from a different perspective, you might say that a proof that mostly uses auto is much simpler, right? Ideally, it's just one step of auto. And in fact, that would count as the simplest according to your metric of proof length. Have you looked at experiments where you either encourage or discourage the amount of automation that's being used in the proofs?
So no, we didn't yet, but we are currently working on a project that is kind of trying to do that, like trying to look at different style of proof that you can do and see how it impacts the results of the LLMs. So, but that's a very good point. Yeah. And also for this particular experiment, like we are using off-the-shelf LLM, so we could, the only lever that we have, as in the previous talk, is the prompt. So we could try to say, please don't use automation, but that's pretty much all we can. We can also say there will be consequences with an exclamation mark.
Yeah, or you could maybe, just as you have the multiple passes where you'll later fill it in, you could say use automation at first and then remove that and ask it to fill those parts in with that.
Yeah, that is true. So we could also change the beam search heuristics to do that. Yeah. Thanks.
Okay, so thank you for the great talk. I have two small questions. So first of all, with the good outlier that you had, wasn't it the case that the proof was really similar to one of the other proofs in the context you gave to the model? Wasn't it the case that it was really similar to something else?
Yeah, so maybe that was not clear. So we thought, no, it's the other one. So we thought about that, and the context that we give to the LLM, we remove all the proofs. There is no proof in the context.
Oh, so there are only statements.
Yeah, only statements.
Okay,
and
it wasn't clear. Okay.
Yeah, sorry about that.
And okay, the second question is, if you possess, don't you have plans to confirm Pitang to MCP protocol? Have you heard of MCP protocols, MCP servers? The protocol of interaction between the AI agent for like easy creation of new AI agents for them to communicate with some server through a specified protocol.
Yeah, okay. So we did not do that. We try to be as lightweight as possible with Pitang. So it's just using basic JSON RPC through TCP. So it's as light as it can be at this point, but we will check the MCP protocol.
I mean, it could be a good idea to confirm Pitang to MCP, so that would give a space for more AI agents.
Yeah, that is true. I'll talk to Emilio about that. Thanks for the recommendation.
Yeah, I also had a question on one of the early slides. You had these steps: explain, reason, and formalize, and then there was just reason and formalize. Was this an optimization to save costs or something like this, or did I understand this right? Or
no, it's just an artifact of the slides because I don't like to put too much stuff in the slides, and so I just cut. Like you should think about a long reasoning chain here, starting with explaining.
Okay, and the explain step, does it reformulate the theorem statement in natural language?
Yes.
Okay, so that's the explain step. Or is there more to it?
I mean, that can be expensive, but we did not measure how much token we spent on re-explaining the theorem compared to formalizing a proof sketch. This is not.
Sorry. I meant this explain step. Is it just translating the theorem statement into natural language, or is there more happening there?
No, we are doing everything at once. We just control the prompt to the LLM, and the prompt says, here is a Rocq statement or Rocq goal. Please explain it, formulate a proof, and then synthesize the corresponding Rocq code.
Okay.
We're at time. Let's thank Guillaume again for a really stimulating talk.